Hello, people. This is Bob Hardage speaking to you. And you see the title of the material that we're going to be going through. We're going to be looking at turbidite systems in the Permian Basin in West Texas. We're going to really try to emphasize here some applications of unsupervised machine learning. And I'm going to leave the impression with you, if I can, that it looks like what we're going to be seeing as a product of this machine learning exercise is the fabric and the internal architecture of those turbidites. All right, we'll take this quick look here at the Midland Basin, which is one of the three basins that are in the greater Permian Basin. And you'll see that this is in far west Texas. Here is the state line between Texas and New Mexico. This is a very large basin. Look down here at the scale. That's an 80-kilometer bar there. So roughly in the north-south direction, it's like 300 kilometers north-south. It's 80 to 100 kilometers east-west. And there is a very extensive turbidite system in this basin, and that's where the majority of the unconventional reservoir drilling has been occurring in the United States for several years. These turbidites systems generally move from north to south. That's just a cartoon here drawn there showing you that general concept. The data that we're going to be, seismic data we're going to be looking at, this little bluish colored rectangle is the location of those 3D data. And this dashed line shows the outline of the basin. And if you'll notice here, there is really a channel here. It's called the San Simon channel. And I want to point that out because the sediment supply that creates all of these underwater avalanches and earthquakes, that generates these turbidite systems, a lot of that sediment supply appears to be delivered into the basin from the area of this San Simon channel here, and kind of get an idea of where that channel is relative to the position of the seismic data. Here's a very general cartoon showing what some of these underwater avalanches look like. And I searched around to find one I thought would be most appropriate for the data we're going to be looking at. There's no scale shown on this, but these can be huge. Their width can be, several kilometers across, and some of them can be very small, like one shown over there to the right. But there are three general features here that I want to point out to you that we will see again when we start looking at some of data products created by machine learning. Look at these red lines here that run parallel to the direction of the sediment flow. You see three of them there, and those are shear lineations that are internal to many turbidite systems. Then, secondly, look here. There's many lobes that are shown, and we're going to see features in, again, the data products we'll be looking at here that appear to be these frontal lobes on successions, the front boundary of those lobes. And you can see here we have 1, 2, 3, 4, and of course a fifth one over there. And these are anomalies that you'll see in the data that are perpendicular to the movement of the sediment, all right? Then internal, third thing that we want to look at to these landslide accumulations are these foldings that go on inside as you get the tumbling action of an avalanche moving down slope. Here's some log data kind of showing you what the detail of this huge Wolfberry turbidite system looks like in the Midland Basin. These 1, 2, and 3 numbered here, those are 3 wells. They're a long distance apart, roughly 6 or 8 kilometers between successive wells. And this is the top of what's called the Wolfberry turbidite system. Stratigraphically, it's a Sprayberry system, and it goes down to the spray barrier. Here's the Dean way down here. Now then, these at this point where we are in the Midland Basin, these turbidites have stacked to a thickness of more than 2,000 feet. And so to not compress the logs too much, we break it here. This is the top half of the logs. Here's the bottom half of the logs, and you'll see the Dean here. It's repeated over here. So this top portion over here, it begins, somewhere right up here in the middle, Leonard. And then the Wolf Camp is the bottom unit of this turbidite system that we're going to be looking at. I think there's turbidite accumulations extending below what's shown here as the Wolf Camp. But that's how these accepted stratigraphic names that you see here for these formations, they were combined to describe this whole top to bottom interval of turbidites. Here's the Wolf Camp. They took the first part of that word wolf, put it here. Then they took the last half of sprayberry, put it there. And so that when you hear the term wolfberry, it's talking about this huge sprayberry, top sprayberry to base Wolf Camp system of turbidites that occur in the Midland Basin and in its companion basin, the Delaware Basin, just immediately to the west of it. I'm going to give you a quick look here at some east-west profiles through the direct P image. That's the top one, PP. And then down here is the same image pulled out of the vertical geophone data, which is the converted P. And it has a shear wave component in it. That's going to be very important about seeing different features internal to some rock systems. So if you look at these two images, number one, the thing that grabs you is they don't look alike at all. And we're going to explore why they look so differently. But just make a quick comment here. I talked about this internal folding that you would see internally to turbidites. Well, you can see pretty good representation of this very complex downlapping, onlapping progradation that's going on. It's well revealed in the upper part of the wolfberry system. And if you look on down deeper, you can see continuing evidence of it. It's a little bit more compressed in its vertical dimensions. You come back up here to the PP data, and there are these internal foldings and internal complexity are far more subdued in this PP image than they are in the converted P image. And again, I hope to kind of give you a technical explanation as to why that is happening. But here's a quick look at the data that we're going to be analyzing. And now the analysis process unsupervised machine learning, I reduce it to these three key steps here. Others may do it differently, but we'll look at it from my point of view this time. That first we do a principal component analysis, which we just abbreviate as a PCA. Then we create self-organizing map or maps, call those SOMs. And then last, we try to look at some geobodies that are expressed in these SOM maps. And the boxes at the bottom basically tell you what you're trying to accomplish in each of these steps. So we'll start out here and spend some time talking about PCA. And what we're attempting to do here is to establish the rank order of the importance of seismic attributes that are embedded in the actual wiggle trace data. I have here a little automation that has been developed by the staff within Geophysical Insights that I think will be helpful on helping you see how these principal components begin to describe the data, a complex data set in a simplified way. So here is a set of data, only two-dimensional data. And I've already told you that we're going to be working with 16-dimensional data. But here's two-dimensional data. And here's the first question you ask. What's the largest variation in these data? Now, variation simply means that's another term for information. So principal components, we're going to get into they're going to translate and be re-expressed with the language of eigenvectors and eigenvalues here very, very quickly. And of course, a vector is going to be a straight line. So what we're trying to do is to find a straight line that goes through these data that describes the largest variation that is in the data. And that's not too hard to do. There it is, the red line. And that then is the first principal component. It got the largest variation within that data set. So now we ask this question down here at the bottom, what's the second largest variation in the data? Okay, somebody might say, well, I would draw a line down here at an angle like that, and I'd almost get as many points as that red line did. Here you run into another restriction that's enforced by the mathematics of principal component analysis, and that is that each principal component has to be orthogonal to its companion principal components. Therefore, when we ask this question, what's the second largest variation, we should say it's got to be perpendicular to the red line. And so we'd choose the green. And there's the second principal component. So what we have here now is the eigenvector. That's showing the direction of the line that shows this variance in the data, or the spread that's in values that's in the data. And the eigenvalue, it's a number that gives you a quantitative measure of what that variance is. All right, now then, the concept of principal components, is pretty easy to visualize in 2D space, but I still want to bring to your mind we're talking about a 16D space. So I'm just going to up the dimension only by 1 in this little PowerPoint here, and we're going to say that the big light blue blob there, that represents 16D attribute space. However dimensions you have, that's how many principal components you will also have. Therefore, there's going to be 16 principal components needed to describe this 16-dimensional data. And PC1 is just that direction in that space that spans the largest variance in the data, just like the little 2-dimensional exercise we went through. And I just draw a straight line there to represent. Then PC2, just like we did in the previous 2D example, it's going to be the direction in the space that spans the next largest variance in the data, with the restriction that that variance has to be normal to PC1. And so I drew it like this. Now then we're going to go up 3 dimensions. So now we got to find PC3, and here is the major constraint on it. PC3 has to be normal to PC1 and PC2. Well, I can draw that. But now PC4, it's got to be passing through the data space, the attribute space, in a direction that is normal to all of the principal components that preceded it. So I don't know how to draw PC4 on a 2-dimensional diagram. So here now is the first principal component in the data that we're going to be looking at. And I need to hasten here and point out that over here in the far right, you see a third set of seismic data, PSV. All I've talked about up to this point is the direct P here, the converted P here. Yes, we had 3-component geophones recorded these data, and we could record PSV data. But will take me just a few slides here, but I will eventually show you that we have to ignore and walk away from the PSV data, and I'll show you why. And before we go on, that lets me then go back to this converted P data here, that this SVP image should be identical to the PSV image. And in the testing that has been done since this very first data set that the converted P was ever calculated for that we're going to be looking at, that's a true statement. Those two images are identical, PSV, SVP. But the beautiful thing about this is it's taken out of the vertical geophone data, and the downgoing SV is generated by P source. And so this converted P data, it's available to all of you. If you have any traditional seismic data generated by P source, recorded by vertical geophones, you have this SVP data. And you just got to learn how to pull it out and use it. Enough of that. Now then, what I'm trying to show here is the rank order of the importance of these instantaneous attributes that were calculated. And if you look across these, you'll see the consistency in the attribute that played its important place in contributing information about the particular image, whether direct P, converted P, or converted S over here. And we'll look at just one more. This is the second principal component for those seismic data. And if you look here at the first three, you can see they're identical for all sets of all three wave modes that we have embedded in the data. These percentages down here, you're probably reading them. They're giving you an idea. If you add up the contributions of information provided by these attributes, you're getting this much of the total information that's embedded in the data that are shown by these bottom percentages here. And this now shows kind of a picture of the entire 16 attributes that I dealt with. And so the amount of information contributed by principal component 1, you can see that's about 18% of the total information. And principal component 2, yeah, what it added was the difference between the peak of 1 and 2. Subtract that, and you get what 2 contributed. And so this is actually showing you how information grows as you expand the number of principal components that you're using for study. And you can cut this off, wherever you want to. You can say, hey, if I get up to 90% here, I'm not going to worry about this stuff over here. It's not going to contribute anything of significance, and that are shown by the blue bars. And some want to be more aggressive and say, hey, if I get 80% of the information, I'm good. And so there's differences of opinion about how far you want to go in determining how many principal components you want to use in your analysis. And everybody's going to have a different opinion. And all I can tell you to do is just calculate them, do them, look at the result, redo it again with a different set of numbers for the population of the principal components you want to use, and develop your own comfort level with where you want the cutoff level to be as to how far you're going to go in using these principal components that you calculate. Now then, this may be, most important. You can't get to these self-organized maps without you have the principal component analysis done. But once people make self-organized maps, why they seem to absolutely fall in love with them. And what those maps do is what's described down here in this box at the bottom. It is a procedure that migrates neurons to data clusters. I mentioned natural clusters. I really should take that word data out and replace it with natural, because data clusters probably best refer to the input data that generated all the attributes. And so this is an intriguing creation here that when we're going to be looking at what these neurons create in the data that are describing the Midland Basin turbidites here. Again, just to refresh here, what we looked at as the original wiggle trace input that was used here the direct P. This is inline 63, inline 63 down here for the converted P. We've looked at that once, just wanted to flash it up one more time because the next thing that comes on the screen is going to be that same inline vertical slice through the self-organized maps of these two data volumes. So here it is. Here is a SOM profile along inline 63 in the PP data, and here is inline 63 in the converted P data down here. And now then you immediately say, what are the colors? What are the colors? And we're going to really focus on what the colors are. I don't have the color map here. I may argue with myself whether I need to do that, but for this presentation, I decided not to show it here. But each of these colors here is going to show you where a neuron searched through this volume and found certain unique combinations of instantaneous attributes. And when it found them again, it colored it again, it colored it again. And so this is now beginning to show you where there are specific combinations of instantaneous attributes. And this is where you're now starting to get your first look at, hey, am I now beginning to see the internal fabric of these units that are stacking up here in this junk pile? That's a good synonym for a turbidite system. It is a trash dump, and you don't know what specific objects you're going to be looking for in a trash dump. And so I don't get too hung up here on looking at searching for a particular kind of geobody, but we are going to be really concerned about how are the mineralogy mixtures distributed throughout this trash dump. We're going to go now and look at horizontal slices through the SOM volumes, and I'm going to go a slice here that's about a third of the way down from the top of the Wolfberry system. Make a horizontal slice that's about halfway down the turbidite system, and then a third one that's about a third of the way from the bottom. Do that for both of these, the direct P and the converted P. And now then, this is the shallower horizontal slices, about 1/3 of a distance into the Wolfberry interval. And I told you we had PSV data. Now you're getting your first look at PSV data. And here's the direct P, and here is a converted P. And I've made you the statement that the converted P and the converted S, they should be identical data. And this says it's far from it. Some of you bright people see a problem with these data here that you don't see with these over here. First of all, let me say that the San Simon channel, if you kind of remember the map that I showed you when we started, it's northwest. It's kind of in that direction, away from each of these displays that we have. Keep that in mind. But now then, look at this PSV map here. This is the source line direction. This is the receiver lines. Look at the straight edges here. Straight edge along the receiver lines, straight edges along source lines. That is the classic, evidence that you have an acquisition footprint. There is a huge acquisition footprint embedded in the PSV data, and it's not in these converted P data. Now, hey, here's another straight edge over here. Is that a problem? No. You see, it is not related. Its direction is not related to the direction of the source lines, the directions of the receiver lines. So that has nothing to do with an acquisition footprint, that straight edge. But remember that I told you that one of the features that you'd find in the turbidite systems were linear shears that went down the length of the direction of sediment flow. And that's why I emphasized a moment ago that likely the sediment flow from the San Simon channel is coming in this direction. So I propose that that's what we're looking at here is a linear shear. And you can see another boundary up here, just looking at the colors. Now be patient about the colors. We're going to get soon here looking in detail what these colors mean. Now then, let's go over to the converted P. So here is a potentially a shear here. It's over here too. It goes right there. You see how it terminates these colors that are going roughly from southwest to northeast, roughly. So their terminations, are essentially the same as this. This possible linear shear edge here, I can sort of find some evidence that it's over here too. But here's the important thing that I see in in this map of the converted P data, and that's these units that are going orthogonal to the sediment flow is this direction, but we got these features that are perpendicular to it, and those are the front edges of those lobes that I was trying to show you when we started, with the cartoon map of what a submarine landslide looked like. So we're already seeing here that I think powerful evidence in the broad generalities of the architecture of the turbidites. We're seeing it. We're seeing the front lobes. We're seeing the linear shears. So this is 1/3 of the way in. We go half the way down into the Wolfberry system. The PSV data, they still have an acquisition footprint. All these straight edges here, that's meaningless. They just cannot follow source lines and receiver lines and be true geology. And the PP gets a little bit more cluttered, somewhat disorganized. The converted P, we continue to see what, I'm tentatively interpreting these features that are basically perpendicular to the trend that the sediment would be moving. It looks like we're still seeing these frontal boundaries of a sequence of depositional lobes. And now then we go down pretty close to the bottom of the system. And again, the PSV still has this acquisition footprint that now then the straight effects are pretty well being dominated by receiver line directions. And again, there's quite a bit of clutter in here, but I'd ask you, what does the internal architecture of a junk pile look like? Well, anything you want it to be. If you could hang this probably on a gallery of modern art and title it Riot at the Paint Factory, and people might buy it. Now, here though, the SV, the converted P, it's consistently staying with, look here at my frontal lobes that are crossing this, showing you that the direction of flow is probably that way. And you sort of get the impression here of a shear edge again too, Now, we ask ourselves, I think rightly so, why are the direct P and the converted P images so different? These, I'm going to show you some work here that a couple of colleagues of mine at the Bureau of Economic Geology did, Scott Hamlin and Robert Baumgartner. This is very meticulous work. They went to collected 200 cores through the turbidite Wolfberry turbidite systems. We have many more, hundreds and hundreds of those cores in the Bureau core storage facility. But they then cut a huge number of thin sections and examined those thin sections under scanning electron microscope and made the mineralogy counts. And this is some of their mineralogy counts, the famous triangle plots that sedimentologists do. And in this case, the three triangles are carbonate, clay, and quartz. And so if a data point is up here, it's 100% quartz. If a data point is, say, right here, like that blue one, why it's going to be 90% carbonate, and it's going to be about 5% of clay. The clay line would be 0 here. So you can see that all these three percentages are going to add up to be 100% total composition of the thin section that they were looking at. But the reason I point this out is to emphasize the high variability of the mineralogy mixtures that are in these Wolfberry turbidite systems, and probably in almost all turbidite systems. But I'll freely admit this is the Wolfberry is the only one I've really studied in any depth at all. But what we're going to do something interesting with those kind of data. We're going to do a little quick numerical calculation. Go over here to panel C, look at that. This is going to be a little model that we're going to calculate reflection coefficients for. We've got a cap rock that's going to be a uniform layer at the top. And here down in panel E, that's going to be the properties that we assign to that cap rock. Then below that, this is our turbidite here. Very low porosity. In fact, that porosity is probably too high for most of the turbidite units. And we say those are lithofaces 1, 2, and 3. All right, here's lithofaces 1, 2, 3. And we put different percentages of the key minerals. And these percentages will add up to be 100%. Now, I had a very brilliant rock physicist who worked for me, Deanna Salva. Some of you may know Deanna. And she had the skill of taking these minerals, their stiffness coefficients, and depending on the percentage of minerals that were in the mix, assigning those stiffness coefficients and calculating the stiffness coefficient for the total rock. And once that was done, then you could start calculating reflection coefficients. And those are going to be up here in panels A and B. So here's the PP reflection coefficients. And these circle numbers refer back down here to the lithofaces. So lithofaces 1 and 2, they basically, a P wave will not see that boundary. They basically are a 0 reflection coefficient. But look at it, the converted P. They're huge reflection coefficients, 4 and 5%. And so these two, converted P sees the boundary, direct P says there's nothing there. Now then, look at lithofaces 3. Good, solid, reflectivity for the direct P. Converted P, I don't see that. It's 0. You're lying to me, cousin direct P. There's nothing there. So this is the key point. PP and SVP data see different rock boundaries, and both of the images are right. It's that second statement, that seismic stratigraphers, have trouble grasping. Well, how am I going to integrate that into my normal practice of seismic stratigraphy? The jury's still out on that, but you cannot argue against the fact here that is what happened. I've seen this evidence in many places, in many basins, many rock systems. And so now then, we're getting here close to the end of the machine learning applications, and here's where it really gets down to be interesting. We're going to start looking really into the interior of these self-organizing maps and trying to see if we can detect something that an object that we really recognize as a piece of geology. If we do, that's a geobody. And if we can't identify it with geology, then it's just an object. And I fear that's going to be the problem looking in the interior of turbidites, because I'll pose the question again. If you look in the interior of a junk pile, of a city's trash dump, what would you find? You can find everything. And so you don't know what you may indeed pull out a geobody, but what is it? You never saw anything like it before? No, I haven't seen a lot of the garbage that you would see in the chaotic mess that you would have in a massive landslide, and particularly an underwater landslide. So we introduce now some more terminology about, and that's about winning neurons. And a winning neuron is a multidimensional vector. And that vector will realize or reveal to you these natural clusters. So it's a natural cluster, a natural cluster, a natural cluster, a natural cluster. But that cluster can indicate a variety of things. It can be a single geobody. It can be several geobodies. It can be only a part of one geobody. Or it may be a cluster that several winning neurons, love it and want to have a part of it. And then you got these other two possibilities here at the bottom. So what I'm showing you here is a horizontal slice through the DirectP self-organized map. And the display on the left, that shows the community of winning neurons that were used to search through the turbidite seismic data. And I arbitrarily chose 64 neurons. You can define the number you want to use. So I'm using 64. And where I'm holding the pointer now, that's winning neuron 1, and you can see they go across, and it's a system of abutted hexagons over here to 8, and they end up here at 64. So what we're going, in that slice, the horizontal slice through the DirectP data, we see all neurons are active here in that slice. But now then, we are going to do something special. We're going to choose just neuron 28, which I'm emphasizing here with the pointer, and then we're going to emphasize winning neuron 35, and then we're going to emphasize winning neuron 26. And now I'm going to go counterclockwise and show you an important connection between those three winning neurons. So I'm on 26 now. I'll go counterclockwise. There's 28, and there's 35, and I'm back to 26. So I'm going to circle. And what is common here between 26 here, 28 here, and 35 there? This guy in the center, 27. So these winning neurons, they share information across their boundaries, just like the neurons in the human brain do. And so it is usually found that neurons that are close together tend to give you similar kinds of data. There's probably going to be exceptions to that, but let me show you how it works in this case. So now we're going to display just winning neuron 28, and here it is. And there's where the winning neuron 28 says, this is where I exist in this particular horizontal slice. And these are natural clusters. They may or may not be a geobody, but they are certainly natural clusters. And I am now thinking that these are distinct mineralogy mixtures in the sediment that's being depicted here by this particular horizontal slice. That's a personal opinion. I can't prove that 100% yet, but that's a working hypothesis. Now then, we say, okay, now then, let's add neuron 35. So here's 28 and 35 together. And you see how closely neuron 35 fills in, nestles up just as close as it can, in many cases, but not in all cases, to its companion 28. And now then we add 26, and it's a light green color, like so here, and it does the same thing. It tends to nestle up more to the dark green, it appears, than to the brown, but in some cases it gets, I think I saw somewhere it got close to the brown, but it's collectively now we're beginning to build the internal structure of that garbage dump. And I'll point out here, these white arrows are again showing the direction of the sediment flow that's coming in, the most likely direction that is coming in. And again, you can see basically a straight edge there, like a shear, and a straight edge this way, which is possibly a shear that's kind of off kilter from the main direction of the sediment flow movement. Now then, we're going to do the same thing, but this time with the converted P data. And here are its map of 64 winning neurons and different colors. You can make the colors whatever you want. And sometimes, after you make them and you look at your map, you think, good night, that's a terrible choice for a color map, and redo it. But in this case, I'm going to show you 3 more winning neurons and choose them a little bit differently. First, we're going to choose number 40, which is right here. And then we're going to choose number 30, which is right here. But you see, they kind of communicate between each other because they share boundaries with 31 here. So I'm going to jump way over here to 25. You can't see 25. White numbers on that yellow background. You can't read the numbers. But where I'm holding the pointer now, that is winning neuron 25. And so we now then look at 40, which is sort of a dark brown color, and here are where its natural clusters are. They're scattered around, some of them rather significant and organized, some, pretty disruptive and helter-skelter, perhaps. And then we add to that number 30, which is a lighter brownish color. And notice how it joins in some cases and really extends the cluster into maybe here's an example where it's taking 2 winning neurons, to build a geobody. Look at that one there and that one there, and we come down here and you see the number 30 winning neuron really continued that distribution of whatever those natural clusters were. But now then we add in 25 and see it was way over here in no contact with them. And 25, the yellow, see, it does not contribute to these people. So you can kind of see how these self-organized maps let you sort of go in with a scalpel and a microscope and really look at the architecture and if you of whatever your depositional system is. In this case, it's turbidites. And if you come up with a hypothesis that you think I have some evidence that maybe these neurons are also telling me something about mineralogy mixtures in the turbidites, and that's a big deal to, I think, to engineers who want to know how to frack those rocks. Why then this is a way to look at that hypothesis, and if you have a sufficient will control, you can prove that hey, it's got some legs, it seems to work, or no, it's a blind alley. Go away from it. And I simply don't have will control in this case to prove the point. We want to look just real quickly here at the instantaneous attributes that form a winning neuron 40 and 30, and look at that. They're exactly the same and essentially the same percentages. So yeah, they are individual neurons, but they are a heck of a lot alike in their internal architectural structure. Neuron 25, totally different animal. It has bandwidth here, which is also in these two here. But other than that, it's got a totally different set of instantaneous attributes in which it embeds its information. And so I'm going to stop at this point and just make this really quick summary. You've seen the first ever SVP image made. You can check the geophysical literature. I've done it. I've had students do it. There is no example of SVP made from a P-wave source in vertical geophones until the data that you've seen right here. And I say they're free there. Why? Because if you got legacy PP data, you can go back and reprocess data. You don't have to spend a penny for data acquisition. In fact, the data that we used in this example was recorded, I believe it was 9 years before we did this work. Then I've tried to demonstrate to you that direct P and converted P modes have different reflectivity behaviors at the same boundary. Therefore, they create different images, and both images are correct. And that's going to be true regardless of which two P-wave modes and S-wave modes you compare, that they're going to be different images. And if everything's done right, both images are going to be correct. Now, this is a hypothesis here. I'll emphasize that again, that these self-organized, these SOM maps that I've shown you, they appear to me to be revealing changes in the mineralogy of these turbidite units. And they certainly are showing the architecture, I think, the internal architecture. And so I took the sidebar, that's an important point to show you that direct P reflections, they're affected by different mineralogy changes than our converted P reflections. Most of this work is in a paper that you can find here. This is the reference to it in Interpretation, Volume 8, back in November 2020. This will be when it was published, and you may find value in that paper. So with that, I close down, and we'll take any questions.